Ever wonder what actually keeps our digital world buzzing, humming, and, well, sometimes even thinking? It's not just the internet itself, right? It's the sheer mind-boggling amount of energy powering our AI.
Absolutely.
Think about it. Your smart speaker listening for commands, your streaming services suggesting your next binge, or even just asking ChatGPT a quick question.
Yeah, all those things.
They're all running on incredibly powerful but also incredibly power-hungry systems. And this insatiable energy demand of modern computing, especially AI, it's becoming a massive problem.
It really is.
I mean, if all the data centers in the world formed their own country, they'd be, well, let's just say they'd need a truly staggering number of power outlets.
That's a good way to put it.
Yeah.
And it's absolutely true. The numbers are startling.
Oh, yeah.
There was a comprehensive review in Chemical Reviews by researchers Shreyash Hadke, Mina Kang, Vinod K. Sangwan, and Mark C. Hersum from places like Northwestern University.
Okay.
They found that global data centers consumed over 200 terawatt hours of electricity back in 2022.
200 terawatt hours? That sounds like a lot.
It is. It's more electricity than entire countries use in a year.
Wow.
And projections, they show that by 2030, just communication technology could contribute nearly a quarter, like 23%, of global greenhouse gas emissions.
A quarter? Just from communication tech?
Yeah. And a huge part of this energy drain, it comes from a fundamental inefficiency in, traditional silicon hardware.
Right.
That's what we call the memory wall, or sometimes the von Neumann bottleneck.
Okay, the memory wall. What's that exactly?
Well, think of it like this. Your computer's brain, the processor, and its memory. They're in two different rooms.
Ah, okay.
And they're constantly shouting information back and forth, wasting energy and time with every single data transfer. It's just not efficient.
Okay, got it. So we have this huge energy problem, this bottleneck. But what if we could build computers that didn't just think like human brains, but actually worked like them, using just like a tiny fraction of the power? Is that even possible? I mean, what does brain-inspired computing truly mean, and how close are we?
That's exactly the mission.
Oh.
We're talking about brain-inspired computing hardware. And the unsung heroes here are something quite remarkable. Two-dimensional materials.
Two-dimensional materials, okay.
Yeah, these atomically thin substances are offering a radically low-energy alternative to conventional silicon. They could potentially revolutionize how we approach AI.
So that's what this deep dive is about today.
Precisely. We're exploring how these incredible materials are mimicking our own biology to create smarter, vastly more efficient computing systems.
Okay, so trying to build computers like brains. But what makes our own brains such an efficiency marvel in the first place? Why are they so good?
It's fascinating, really, just how incredibly efficient our brains are. I mean, neurons fire much slower than computer chips. We're talking millisecond timescales.
Right, much slower.
But despite that, the human brain operates on a paltry 20 watts of power.
20 watts, that's it.
That's it. Less than a dim light bulb.
That's amazing.
And it's not just a happy accident, Our brains achieve this because they essentially combine memory and processing in the same place, the neurons themselves.
Ah, so no separate rooms like the computers.
Exactly. Plus, they're hyper-connected. You've got over 100 billion neurons talking to each other through over 100 trillion synapses.
Whoa.
And they process information in parallel. It's the ultimate in-memory computing system. It allows for continuous learning, robust performance, all without wasting energy shuttling data back and forth.
So the stark opposite of that memory wall you mentioned.
The complete opposite. And here's a wow fact that really drives home the urgency.
Okay.
While our brains are amazingly efficient, AI computing usage has been dramatically accelerating. It's been doubling every 3 to 4 months in the past decade.
Every few months.
Yes. Far, far outpacing the traditional improvements we've seen in computer chips with Moore's law.
That's unsustainable. That comparison is staggering.
So, okay, the brain is the gold standard for efficiency.
Yeah.
What does this mean for building better computers? And tell me more about these two-dimensional materials. What are they?
Well, imagine a material so thin, it's just a few atoms thick, literally two-dimensional.
Like a sheet of paper,
Yeah.
but infinitely thinner.
Exactly. Almost transparent, but capable of these mind-bending electrical tricks. That's what we're talking about with 2D materials.
So like nature's own super thin high-tech Legos for microchips.
That's a great way to think about it, yeah. Materials like graphene, you've probably heard of that one,
Mm-hmm.
or molybdenum disulfide, usually called MOS2, and hexagonal boron nitride. or HBN, these are prime examples.
Okay.
Their atomically thin nature gives them unique electronic structures, incredible flexibility, and lets them be integrated into circuits in ways silicon just can't.
Flexibility, like they can bend.
Yeah, literally bend. And this broad range of properties makes them ideal candidates to break through those computing bottlenecks, that memory wall we've been struggling with. Okay, so if we want to build a brain-inspired computer, we need to mimic the brain's building blocks, its synapses and its neurons. Let's start with those connections. How do these 2D materials help build artificial versions?
This is where these 2D materials become truly foundational. They can form something called memristors.
Memristors, like memory resistors.
Exactly, a portmanteau. They're essentially artificial synapses. And the real insight here is that memristors store and process information in the very same place.
Like the brain.
Just like in our brains. They're not just making chips faster, they're fundamentally breaking free from that memory wall. They basically remember how much current has passed through them, acting as a dynamic connection strength.
Okay, so they learn.
In a way, yes. For these artificial synapses to be really effective, they need to store information without constant power that's non-volatile memory.
Right, non-volatile.
And they need to be able to learn by adjusting their connection strength, their weight, in a very precise, linear, and symmetrical way. Much like our brains strengthen or weaken connections between neurons.
And 2D materials can do this.
Research, like the work cited in that chemical reviews paper, highlights that 2D materials enable memristors with ultra-fast switching speeds, often less than 10 nanoseconds.
Wow, that's fast.
And incredible endurance, sometimes over 10 to the power of 15 cycles.
So they can switch billions and billions of times without wearing out.
Precisely. They can remember and adjust their memory over and over. Devices using MOS2 and HBN as active layers, for instance, have shown exceptional memory characteristics.
That's astounding. So they're giving computers this integrated storage and processing, very efficient. But what about the other half, the neurons, the cells that fire signals? How do 2D materials help create artificial neurons?
Yeah, this is where it gets really interesting, I think. Beyond just memory, 2D materials are being used to create artificial neurons that actually fire like biological ones.
Not just on-off switches.
No, not simple switches. They can integrate multiple signals coming in, reach a specific threshold, and then spike an output. It mimics how your brain cells make decisions. Researchers are exploring different types, like integrate and fire, or IF neurons, and leaky integrate and fire, LIF neurons, which are a bit more complex.
Right.
And one significant breakthrough, also highlighted in that review, involved a novel type of transistor. They called it a Gaussian heterojunction transistor, or GEET.
GEET? Catchy.
Yeah, maybe. This device cleverly combines different 2D materials, like that N-type MOS2 and P-type carbon nanotubes.
Okay.
And when they integrated these GETs into circuits, researchers showed they could mimic the complex spiking behaviors of biological neurons. Things like simple tonic spiking, or even intricate phasic bursting.
So it's like giving computers their own neural impulses.
Kind of, yeah, all within these incredibly thin materials. It opens up completely new possibilities for how we process information.
So we're not just building better components, we're fundamentally rethinking how entire systems operate. When you bring these artificial synapses and neurons together, that's neuromorphic computing, right?
Exactly.
What are some of the most exciting breakthroughs there?
Right, this is where the real magic happens. Performing calculations directly where data is stored in memory analog computing.
Bypassing the memory wall.
Completely bypassing it. And we're seeing some incredible progress here. Take supervised learning, for example, basically, teaching a computer by showing it examples.
Like recognizing images.
Exactly. A study by Dada, Trainer, Redwing, and Das, published in Nature Communications in 2022.
Okay.
They demonstrated these all-in-one bio-inspired systems, like crypto systems and IoT edge sensors using MOS2 MEM transistors.
All in one.
Yeah, combining functions. And their simulations achieved a 94% recognition rate for MNIST digit classification. That's a standard test for identifying handwritten digits.
94%, that's pretty good.
It is, especially considering they simulated even with 10% background noise. It shows the potential for high accuracy, even with the inherent variability you get in these new devices. Perfect for smart devices out at the edge of a network.
That's great for smaller, specialized AI tasks. But what about more complex functions, like the core processing in a neural network?
Absolutely. There's work on that too. Another fascinating development focuses on making fundamental AI operations more efficient, like the ReLU activation function.
Relay U, I've heard of that. It's important in neural nets, right?
Very important. It's a key nonlinear step that determines if a neuron fires, and how strongly. Researchers Huang, Liu, Kang, Zheng, Wang, and Zhu reporting in ACS Nano in 2023.
Got it.
They demonstrated a self-activated ReLU function using ambipolar WSE2 charge trap memory.
Self-activate, so the memory does the work.
Essentially, yes.
Yeah.
This allows the memory itself to act like the neuron's processing unit. It eliminates the need for separate, power-hungry activation circuits and dramatically increases efficiency by computing right there in the memory array.
Wow, packing more function into the same spot.
Exactly. And then, in another significant step forward, a team led by Wu described something called a duplex ferroelectric dielectric memory in 2023.
Duplex. Sounds fancy.
Well, imagine a memory that gives you the best of both worlds. It has high endurance so it can handle continuous training.
Okay, learning.
And long-term retention for inference tasks. So it can both learn and remember reliably for a long time.
That's crucial.
Very. They achieved a remarkable 99.86% accuracy in a complex 2D nonlinear localization problem. They showed both training and inference on a single device, which is a key step towards truly integrated brain-inspired chips.
And it's not just about electrical signals anymore, is it? I think you mentioned these materials can even work with light.
That's another really compelling aspect, yeah.
Yeah.
Beyond electrical signals, 2D materials also allow computers to process light directly.
How does that help?
Well, it enables entirely new applications,
Yeah.
like retinamorphic motion detection.
Retinamorphic, like the retina.
Exactly. It mimics how our eyes detect movement, but without needing to convert light into electrical signals first.
Ah, so fewer steps, less energy?
Precisely. It reduces energy consumption even further and opens doors for ultra-efficient vision systems. And here's another wow fact that ties back to that flexibility you asked about. The mechanical flexibility of 2D materials means they could potentially be used in things like neuroprosthetics or soft robotics.
Whoa, really?
Yeah, allowing computers to literally bend and flex with us. You could integrate them directly into our bodies or into responsive environments.
That sounds like science fiction, but it's real science happening now.
It is.
Yeah.
Very real.
But okay, it can't be all smooth sailing. It sounds incredible, but it's not without its hurdles, right?
Yeah.
So what are the biggest challenges? What's stopping this from being in my phone tomorrow?
You're right. It's definitely a marathon, not a sprint. One big challenge is just manufacturing.
Making the stuff.
Making the stuff, yeah. Specifically, making these tiny, perfect materials on a wafer scale. We need to produce them consistently in large quantities and uniformly across large areas.
Wafer scale like current silicon chips.
Exactly. Methods like chemical vapor deposition, or CVD, are advancing but precisely controlling thickness and uniformity across these large areas. It's tricky. The Chemical Reviews paper really highlights how crucial this wafer-scale growth and precise thickness control are. Even one extra atomic layer can change how a device works.
So it's not just making them, but making them perfectly every single time and big enough.
Right. And once they're made, how reliable are they? That's another critical area.
Device reliability.
We need to precisely control defects within these materials. Interestingly, defects can be both a blessing and a curse.
How so?
Well, sometimes specific defects, if you engineer them carefully, can actually help influence how these memristors switch and store information. But uncontrolled defects, they can severely hinder performance.
So you need good defects, not bad ones.
Something like that, yeah. We need a thorough understanding of both defective and defect-free systems to get reliable and reproducible behavior. Plus, for some of the magnetic 2B materials, we need to figure out how to make them work reliably at room temperature.
Ah, not just in super cold lab conditions.
Right. And also achieve ambient stability. Make sure they don't just degrade or react when exposed to normal air. Many of them can be quite reactive.
Okay, manufacturing, reliability. What else? We've got billions, trillions maybe, invested in silicon tech. How do these new 2D devices play nicely with the existing stuff?
That's the huge challenge of heterogeneous integration.
Heterogeneous, mixing different things.
Exactly. It's a bit like trying to merge two completely different construction styles for a single building, without any gaps or weaknesses. You need to overcome issues like chemical residue left over when you transfer the 2D material onto silicon.
Leftover gunk.
Pretty much. And mechanical stress during that transfer process. And ensuring reliable electrical contacts right down at the atomic scale, where even tiny imperfections can break the whole circuit.
Sounds delicate.
It is. But progress is being made there too. There are advanced transfer methods, like dry transfer techniques, that offer more precise placement and better cleanliness compared to the older wet methods. So that's paving the way for more seamless integration down the line.
Okay. So to wrap up this deep dive into the tiny, powerful future of AI, let's hit the key takeaways for everyone listening.
Sounds good.
First, our current AI is incredibly power hungry, the way we're doing it now. We desperately need a new approach to make it sustainable. The energy demands just aren't viable long term.
Agreed. Second, these 2D materials, these amazing atomically thin substances, they offer a radical and, frankly, elegant path towards brain-inspired computing.
Elegant, I like that.
Yeah, they can create devices that mimic how our synapses and neurons work, all in a much more energy-efficient and integrated way than traditional silicon. They
Yeah.
fundamentally break that memory wall.
Right. And third, while there are definitely significant challenges manufacturing these perfect materials, making sure they're reliable, integrating them with silicon, it's not easy.
Not at all.
But the potential is immense. Flexible, compact, super efficient AI chips for everything from, I don't know, smartwatches to self-driving cars, maybe even medical implants. It's huge.
It really is. This isn't just about faster computers. It's about smarter, more intuitive systems.
Yeah.
The journey toward truly brain-inspired general intelligence, AI that can really think and learn like us, it's long. But 2D materials provide fundamental building blocks. This deep dive into 2D materials for neuromorphic computing isn't just about making faster computers. It's about making computing systems that can interact with the world in new, more intuitive ways, really exploiting the complexity we see in biological brains.
So here's a final thought to leave you with. Imagine a future where your smart devices don't just execute commands, but they learn continuously, they adapt fluidly to your needs, and maybe they use less power than a single thought. How might these tiny brain-inspired materials change not just our technology, but the very way we live, think, and interact with the world around us?